Oh, sorry. We're joined today by Diana Powell, who's just joined us here at the ITC as a NASA Sagan Fellow, and she'll be with us here for 2 years before starting a faculty position at the University of Chicago. We're going to hear from Diana about the microphysical insights into protoplanetary disks and exoplanet atmospheres. So I'll now turn it over to Diana.
Awesome. Okay, so hello everyone, and thank you so much for having me. So today I'm really excited to talk with you all about microphysical insights into protoplanetary disks and exoplanet atmospheres. And in this talk, I hope to demonstrate to you why we're closer than ever before to understanding the formation and evolution of planets, in part due to this ongoing microphysical revolution. And so for the purposes of this talk, microphysics refers to the physics that governs the evolution of small particles and the presence of gas. Okay, so the key question behind all of this research is, what is the origin, evolution, and nature of planets? And to address this question, I characterize planets and the planetary material and protoplanetary disks. And in particular, I use theoretical microphysical tools to peer beneath each veil, the veil of each stage of planet formation, and uncover fundamental properties of both disks and atmospheres. Okay. So the general picture of planet formation that has emerged looks more or less like this. So planet formation begins in protoplanetary disks. So these disks constitute the building blocks of planetary systems. Then once the bulk of the disk dissipates, a young planetary system remains. And the second phase is not usually included in diagrams like this, but I'm doing so because it represents a distinct observational stage with unique signatures and observing strategies. And then as time progresses, planets will find relatively stable orbits, and the planetary atmospheres will also evolve. Okay, so this is the general picture. But what I really want to know is, how can we relate these disparate evolutionary stages to learn about the formation, evolution, and nature of the full complement of planetary systems? And we're very lucky to be alive at a time where each of these stages of planetary evolution is undergoing an observational revolution. So we have these unprecedented observations of each of these evolutionary stages. So we can observe protoplanetary disks, such as the disks observed in high resolution shown here. And as a bonus, we can also observe protoplanetary disks undergoing active planet formation, like the PDS-70 system shown here, where you can see 2 points that are thought to be giant planets undergoing accretion. We can also observe young planetary systems directly, like the Beta-Pix system shown in the bottom left. And finally, we now have observations of over 4,000 evolved exoplanets and detailed constraints from solar system planetary science and cosmochemistry. And so with all of these data, this is really the era to start actively connecting planet formation to planetary characterization. And so the way that I approach understanding planet formation and evolution is from the perspective of chemical compositions using microphysics. And so in particular, my research program focuses on using microphysical theoretical tools to determine how chemical compositions of disks relate to that of planets and vice versa. And so while this ongoing observational revolution of both planets and disks represents a really fantastic opportunity to connect planet formation to planetary characterization, it also represents a significant challenge. And so to get a quick idea of why determining the composition of protoplanetary disks is difficult, let's take a quick look at this vertical cross-section. So here the system's host star is on your right, and the disk flares out at larger radii on your left. And so planets form in the disk midplane, which makes this a region of particular interest. However, in the midplane, ice particles are moving radially, which will affect the midplane composition. And this radial motion can eventually cause the ice to reach hotter regions of the disk where they lose their volatile material back to the gas phase, again altering their composition. And at the same time, the gas in the disk is being mixed around and changing the radial composition and vertical composition. And not only are disks constantly in this non-equilibrium state, but to top it all off, there's also gas present in the upper regions of the disk that can be optically thick, such that you don't see emission from the midplane directly. And this is all especially true in the inner regions of disks where we know that planet formation is common. Okay, so determining useful compositions of disks is difficult, but what about planets? And so when determining compositions of planets, a primary source of compositional information comes from atmospheric observations. And so on the left here, I'm showing a collection of emission spectra for directly observed planetary mass objects. And on the right, I'm showing a collection of transmission spectra for tin hot Jupiters, which are highly irradiated Jupiter-like planets. And despite the detail we can observe in these objects' atmospheres, these observations are often hindered by opacity sources, such as clouds and hazes, that can obscure compositional features and other planetary properties. And so what we're probably looking at are atmospheres that look something like these atmospheric slices shown here. So these atmospheres are covered in clouds. And clouds can be low altitude, such that we can observe some unobstructed regions of phase space, or they could be high altitude. And so high altitude clouds will completely obscure signatures of atmospheric composition. And even when clouds are low altitude, they can obscure planetary signatures, they can alter observed gas phase abundances, and influence planetary radiative transfer. And then in addition to the complicating presence of clouds, atmospheres will also evolve. And so both of these cases, both in disks and atmospheres, many of the complications with determining chemical compositions boil down to a need for a better understanding of microphysical processes. And so in this context, I'll remind you that I use microphysics to refer to the evolution of small particles in the presence of gas, where many of the key common processes are shown here. So in the case of atmospheres, microphysics governs the evolution of clouds. And in disks, microphysics governs the evolution of small, icy, or rocky solids. And by the end of this talk, I hope that you'll see how microphysics applies in several different contexts and is crucial in understanding these systems. Okay, so to make the connection between protoplanetary disks and planetary atmospheres, we need better physical models to interpret current and upcoming observations. And I'll argue that microphysics will be important in making this connection, and microphysics might actually be the key to understanding a lot more about the origin, evolution, and nature of planets. And so I'll start by talking about some of the initial work that I've taken towards tying planet formation to planetary characterization. So I'll start by talking about planetary atmospheres with a focus on clouds. I'll then move on to discussing fundamental properties of protoplanetary disks, such as the total amount of mass present in these systems. And then I'll bring the techniques that I've used in the two previous topics together through a discussion of the evolution of carbon monoxide in protoplanetary disks. Okay, so let's talk about clouds. So we all have some intuition about clouds from our familiarity with clouds on Earth. But clouds are important beyond Earth and are in fact the dominant opacity source in most planetary atmospheres. So clouds are important tracers of atmospheric physics, such as mixing and transport. Clouds regulate the planetary climate through regulating radiative transfer and chemistry. And clouds must be understood when determining atmospheric abundances. Also, often the clouds in an atmosphere are the only thing that we can see. So it's therefore an absolute necessity that we understand clouds when we're interpreting planetary atmospheres. And so given this, there's a lot that we can learn about planetary atmospheres through studies of clouds. So it makes sense to understand how clouds evolve and form from first principles. So on the right here, I'm showing an example of some of the outputs that I calculate of cloud properties in planetary atmospheres. So here I'm plotting the mass density of cloud particles as a function of particle size and atmospheric pressure. And so here, each of the different colors indicates a different cloud species. And all of the properties of the cloud particles shown here, such as their particle size distribution and vertical extents in the atmosphere, are calculated from first principles through consideration of the microphysical processes that I've shown here on the left. So this cloud formation model is readily adaptable and widely applicable, and has been used to predict and explain data for a wide range of planets. So I'll show a few quick examples of what I've done with this so far. But before I do that, I really want to emphasize that this model is not a black box. So we've engineered every single key microphysical component and have carefully considered every aspect of cloud formation that is considered in this framework. So we're really not looking at a black box, we're looking at physics. And with this framework, we can predict how clouds will look at different locations on a given planet. So here I've translated calculated cloud properties into transmission spectra that look significantly different in both amplitude and shape between the east and west limbs of the same hot Jupiter. So in black here, I'm showing the calculated transmission spectra on the east and west limbs. In gray, I'm showing the east limb transmission spectra if there were no clouds. And then in blue, I'm showing the opacity continuum due to clouds. So as you can see on the west limb, cloud opacity is significant across a very broad wavelength range, where it flattens the observed transmission spectra. On the east limb, clouds contribute to this muted and sloped optical spectra, and this broad absorption feature in the infrared due to silicate and aluminum clouds, which collaborators and I will probe in JWST cycle 1. And then there's also an intriguing clear window around 3 to 10 microns that could allow us to peer through the clouds. So to really understand the nature and composition of planetary atmospheres, we'll be greatly rewarded by looking at these planets in 3D. So as you can see here, the east limb gives us much more information than other locations on the planet. And these models will become increasingly more useful with the launch of JWST, which will allow us to uncover atmospheric trends across populations of planets. So an example of one such trend that has already been observed in hot Jupiters is shown here. So the day and night side temperatures of hot Jupiters are diagnostics of heat transport processes in their atmospheres. And what we observe is that as their planetary equilibrium temperature increases, the day side temperatures also increase linearly. However, the night side temperatures for this really diverse range of hot Jupiters remains roughly constant, even as their day sides heat up. And so we've modeled the clouds in these atmospheres and found that the constant night side temperatures on hot Jupiters is a natural outcome of the abundant production of spectrally active silicate clouds. So these silicate clouds dominate the atmospheric opacity. And so even accounting for changes in vertical mixing with changes in global circulation that occur as a function of equilibrium temperature, we show that what we're seeing across all of these planets is the silicate cloud top. And so this further demonstrates that clouds shape observations and planetary climate. And so I'm also working on interpreting observations of exoplanets in emission, reflection, and transmission using two-dimensional models of microphysical clouds, where I calculate how cloud properties change as they are vected along a super-rotating equatorial jet of a hot Jupiter. So clouds changing with atmospheric dynamics. And so here I'm showing condensed cloud mass of different cloud species as a function of planetary longitude and pressure. And using these models, we can robustly determine the impact of clouds on high resolution observations and exoplanet phase curves. And this is work that I will continue here and will provide the forward models needed to understand new observations and probe fundamental planetary properties in the JWST era. Okay. So I'd love to talk about clouds more, and especially because they're so important in understanding substellar atmospheres, which is important in constraining planetary properties. But for now, let's turn our attention to protoplanetary disks, which are the locations of planet formation. And I'll start by talking about the interesting question of how much total mass is present in these systems. And so the question of how much mass is in protoplanetary disks is fundamental for planet formation and evolution. So the amount of total mass in the system influences the ultimate mass and composition of formed planets by affecting the evolution of solids and gas that eventually make up the planetary system. So the total disk mass also regulates several favored planet formation pathways, So particularly the processes where the amount of gas, which makes up the bulk of the disk mass, affects the evolution of the solids. And so the question of how much mass is present in these systems needs to be answered so that we can get a handle on the initial conditions of planet formation and how these might vary from system to system. Okay, so the most common tracers of protoplanetary disk properties are dust or different trace gases such as CO gas, as these are relatively easy to observe. Due to a lack of probes or direct probes of the main mass constituent, which is H2 gas, these previous measures of disk mass have relied on some tracer to H2 ratio. However, we know that processes such as grain growth and drift should alter the dust to gas ratio from the typically assumed interstellar medium value. And now several lines of evidence also suggest that gas phase CO, so particularly in the commonly observed upper disk layers, is depleted or missing in disks. So this begs the questions: how can we measure the total disk mass without an assumed tracer to H2 ratio? And also, what is happening to all of the CO? And really getting to the bottom of these questions is of the utmost importance for understanding disk physics and other disk properties, which will allow for an improved understanding of the initial conditions of planet formation. And so I began addressing these questions by considering multi-wavelength observations of disks in the millimeter. So here I'm showing a visualization of observations of the disk around TW Hydra, where here these pictures are of the same disk, but it appears smaller in radius at longer wavelengths. And to introduce some terminology, I refer to the maximum radius in which there's emission at a particular wavelength as a dust line. And as others have suggested, these observations may be signatures of particle drift. So particles drift in disks because the gas feels this outward pressure gradient that causes particles to feel a drag that removes some of their angular momentum and causes them to drift inwards towards their host star. And so we can use these observations of particle drift to trace the aerodynamic properties of the observed particles and determine the total gas mass present in these systems. So we can do this following the simple equation shown here on the right if we know several key quantities. So in particular, if we know the maximum radius and which particles of a given size are present. And so we can infer the particle size if the observed wavelength corresponds to the primary particle size contributing to the observed emission at the disk outer edge. And then we can measure the disk size to determine the radius in which those particles are the maximally sized grains. And so this method allows us to derive the disk surface density without assuming a tracer to H2 ratio, because we really only care about how fast the particles drift, which depends primarily on their size and not on how many particles are present. Okay, so I've applied this model to 7 protoplanetary disks with previous millimeter observations that show decreasing disk radial extent with wavelength. And so here I'm showing some of the observations for 3 out of the 7 disks in our sample. And so we can do a lot with this modeling, but one of the key things that we found is that disk masses are larger than we initially expected. So here on the left, I'm showing total gaseous surface densities in black compared to previous tracer-derived surface densities and the minimum mass solar nebula, which represents the minimum mass required to form our solar system. And so the disks in our sample are 9 to 27% of their host stellar masses. So this is significantly more massive than the minimum mass solar nebula, which is only about 2% of the sun's mass. And these disks are also 2 to 15 times more massive than estimates from optically thin dust emission, assuming an interstellar medium dust to gas ratio. And then for the 3 disks in our sample that have resolved CO emission, our estimates are 3, 40, and 115 times more massive than previously published, indicating that CO depletion is not uniform across different disks. And so these results indicate that dust may be a more robust tracer of total mass because we uncover a reduced gas to dust ratio that's roughly consistent across our sample, while the CO to H2 ratio varies more strongly. And I'll come back to this later in the talk. Okay, so here I'm plotting the tumor Q stability parameter as a function of radius in the outer disk. And so a tumor Q parameter less than approximately 1 is where you would start gravitationally collapsing under your own self-gravity. And so all of the disks in my sample are stable to gravitational collapse, except for one disk which approaches the limit of tumor Q stability. And interestingly, the disk's morphology also shows some indications of features that could be due to gravitational instability in high-resolution images. But note that all of the disks in our sample have low Q values at certain radii. And so we think that when you first form disks, they're accreting because they're marginally unstable, and this marginal instability might be helping to raise spiral arms that throw material onto the star efficiently. And we still think that all of that is going on. But after this early phase of star formation, you really need something like MRI or disk winds to kick in to drive further accretion. And it's really a big mystery how disks are able to accrete efficiently at late times. But maybe if some disks are actually close to gravitational instability, you do not need a lot of these accretion processes to be happening, because at least some disks, so at least the bright massive disks in my sample, seem to maintain much of their mass. And in our modeling thus far, it has not been required to know an expected dust surface density. But given our results, we can now use models of coagulation to compute the dust surface densities. So here I'm showing the surface densities for the disk ft tau, where the blue line is the total gaseous surface density derived using the dust line method. And then the solid black line is the observed dust surface density. And here the dashed lines are dust surface densities derived using analytic and numerical treatments of particle coagulation. And so for the disks in our sample, we derived depleted dust to gas ratios of around 10 to the minus 3, which is a common outcome of models of grain growth and drift. And so in these models, the dust drifted into the inner disk where it undergoes further evolution. But you can also paint a consistent picture here with some of the drifting dust being incorporated into planets over time. And it's worth noting that in these models, the disks formed with an initial dust mass that's a factor of 10 greater than is presently observed. And also, being able to constrain the dust and gaseous surface densities using this method can allow us to empirically constrain the dust opacity, which is particularly exciting because the dust opacity remains one of the largest sources of uncertainty in studies of protoplanetary disks. Okay, so we can learn a lot using this model that I haven't talked about here. So from the aggregate nature of the solid particles that we observe to the nature of the disk morphological features. But overall, here's this new picture of disks where they may be more massive than previously appreciated. So the total dust mass is the same, but the total gas mass is about an order of magnitude larger. And these qualitative changes to models of protoplanetary disks have significant implications for theories of planet formation, particularly for any process where the amount of gas is affecting the evolution of solids. So that will be affected by this picture. And I also want to emphasize that our model does indicate that there was more dust mass at early times, which helps bring agreement between the discrepancy in disk dust masses and the mass of extrasolar systems. Okay, so we've discussed the total mass in disks, but what is happening to all the CO gas in the system, in these systems? And so I'll use my remaining time to discuss this because we really want to know the answer to this question, because CO has been used as a tracer for a broad range of fundamental disk properties, which could be biased if we are assuming that there's more CO relative to H2 than reality. And also because CO is a primary carrier of carbon in protoplanetary disks, and is thus important when we talk about planetary inheritances. And to answer this question, I'll combine the two methods that I've used so far in this talk. So modeling clouds and modeling disks. And I'll start by saying that it's definitely not just my modeling that indicates that CO is depleted in disks. So on the left here, I'm showing the CO abundance in the disk TW Hydra as a function of radius, compared to the abundance that we would expect from observations of the interstellar medium. So you can see that CO gas appears to be significantly depleted. And then the same is true if we look at large samples of disks. So here I'm showing an ALMA survey of disks in Lupus, where the disks span several orders of magnitude in dust mass, but have fairly constant gas masses estimated from CO. So in short, we observe much less CO in disks than we would expect, or than would be predicted using previous disk models. And to address this problem, I've coupled my model for protoplanetary disk properties with an adapted version of the models that I use to study cloud formation in exoplanet atmospheres. And in this context, I'm modeling the formation of ice on dust in disks. And in particular, the nucleation and growth processes in the scheme include the Kelvin effect, which quantifies the stability of particles through considering the strength of the molecular surface bonds. And so I like to think of the Kelvin effect in terms of geometry, where an ice molecule on the surface of a large grain will be able to bond to more neighbors than it would on a small particle that has more curvature. And so in short, the Kelvin effect causes large particles to nucleate and grow more easily. And the particle sizes are important here because they actually regulate the level of depletion that we observe of gas phase CO. So if we approximate a vertical temperature structure in the disk, as shown here on the left, where the disk would be roughly isothermal until it reaches a height where surface layer heating is efficient, then outside of the ice line in the midplane, the disk is cool enough for ice to form on dust grains. So there'll be a region of the disk where ice is stable, and a region where evaporation or photodesorption could occur. So if the ice particles that form in the midplane are small, then they could be lofted to the upper regions and evaporate such that CO gas is not significantly depleted. Well, on the other hand, if the ice particle is large, it can deplete the CO gas in the midplane. And so that's what I'm showing here on the right. So once the initial abundance of CO gas, shown in solid black, is depleted in the midplane, as shown in gray, then there's the steep concentration gradient, which will be smoothed by vertical diffusion. And this could ultimately lead to a level of depletion of CO and the observed upper levels as shown in solid red. And so this is the so-called cold finger effect, which can lead to a large depletion of CO gas in the upper disk. Okay, so let me I should say, so that's the vertical evolution, but the gas and dust in the system evolved radially as well. So let me quickly walk you through this picture of the evolution of CO in disks. So in the outer disk, CO is continually mixed down towards the disk midplane, where efficient ice formation occurs on large particles. These large particles then drift inwards towards their host stars. And once these ice particles drift inwards to the hotter regions of the disk, they release their volatile CO back into the gas phase, and then some interesting cycling of material occurs around the ice line. And then there will also now be an enhanced abundance of CO gas in the inner disk that is accreted onto the host star over time. And so we find good agreement here between our results and observations, as I'm showing in plots B through E. And in our modeling, we find that this process depends strongly on diffusion, which contributes to the observed variance of CO depletion in different disks. So in the large plot here, you can see that the amount of observed depletion in the outer disk depends on the amount of diffusion that is operated in the lifetime of disks. And using this model, I'm able to constrain the solid and gaseous CO inventory at the disk midplane where planets form, and constrain the bulk disk diffusivities and mixing characteristics, and then also resolve inconsistencies in estimates of disk mass using different tracers. So those are three crucial parameters that control planetary formation. And I should also say or note that this process will also be applicable to other volatiles and disks. So the microphysical processes of ice formation both regulates the observed abundances of CO gas and is crucial in determining the radial composition of protoplanetary disks. So something that we'll be working on here is modeling the distribution of other volatiles in disks. And so particularly for species that emit readily and are dominant carriers of oxygen, carbon, and nitrogen, which are important planetary building blocks. And so one of the other things that I'm interested in working on here, so in the vein of connecting planet formation and evolution, is to determine the radial and temporal composition, well, the compositional distribution in protoplanetary disks through modeling observations of different volatile species using my models of ice formation and evolution. And then I will also model the atmospheres of planets in the same planetary system with a detailed accounting for clouds, with an initial focus on young planetary systems. So with the compositional gradient of planets in the same planetary system and the radial and temporal composition of protoplanetary disks, we'll have the ideal sample to systematically relate these two objects. And so we'll be looking at comparable radial distances with as little separation in time as possible. And so with a detailed comparison over several systems like PDS-70, HR8799, and Beta-PIC, as well as a slew of disks, we can begin to get a sense of where these planets are likely to have originated in the disk as a function of radius and time. And so in conclusion, I've talked about understanding substellar atmospheres using cloud microphysics, and I've discussed uncovering fundamental properties of protoplanetary disks using particle aerodynamics and ice formation. So I'll leave my conclusions up here and very happy to take questions.
Yeah, like, no, slowly. Thank you for a really interesting talk, Diana. Yes, like, slowly. We already have a few questions here. The first